In this video, we'll explore the causes and impacts of climate change, focusing on the role of greenhouse gases, how common the current situation is in a historical context, and what we can do to address this global challenge. Before we dive in, let's quickly distinguish between weather and climate. Weather refers to short-term conditions like rain, temperature, and wind, the day-to-day changes we experience. Climate is the long-term average of these conditions over decades. It's important to remember that an unusually cold winter or a rainy year doesn't mean the overall climate trend is changing. Climate looks at the bigger picture, showing long-term shifts in temperatures, rainfall, and wind patterns. Global warming, or climate change, refers to the steady rise in Earth's temperatures. Since the late 19th century, the pre-industrial era, the planet has warmed by about 1.4 degrees Celsius, with much of the increase happening since the 1970s. While global temperatures provide an overall picture, not all regions are warming at the same rate. Land areas, especially in the northern hemisphere, are heating up nearly twice as fast as oceans because land retains less moisture and has a lower capacity to store heat, while oceans absorb more heat and cool via evaporation. The Arctic is warming even faster, up to 3 to 4 times the global average. This is due to processes like the loss of sea ice, which normally reflects sunlight. As the ice melts, darker ocean water absorbs more heat, accelerating the warming in the region. Though 1.4 degrees Celsius may not seem like a big deal, even small increases can lead to major shifts in weather patterns, sea levels, and ecosystems. We'll explore the profound implications of this warming in the following sections. In addition to rising global temperatures, several key indicators show how our climate is changing. Ocean heat content has increased, with the upper layers absorbing much of the excess heat, influencing global weather patterns. Atmosphere, the troposphere is warming, while the stratosphere is cooling, a typical sign of greenhouse gas-induced climate change. Cryosphere, glaciers are shrinking worldwide, with Arctic sea ice declining by 12% per decade. Greenland and Antarctica are losing ice, contributing to rising sea levels. Sea levels, global sea levels have risen about 20 centimeters since 1880, with an accelerated rise of 5 millimeters per year since 1993. Weather patterns, heat waves, changes in rainfall, and more intense hurricanes are becoming more common, driven by warming oceans. Day versus night temperatures, nighttime temperatures are rising faster than daytime temperatures, likely due to increased cloud cover. Animal behavior, animals are shifting migration and breeding patterns in response to warmer temperatures, disrupting ecosystems. All these indicators show that climate change is a long-term trend with widespread impacts. To understand how typical today's climate situation is, we need to look beyond the last 150 years. Scientists utilize various proxies, like tree rings, ice cores, and fossils, to reconstruct Earth's climate over thousands and millions of years. Combining these proxies reveals that, while temperatures gradually declined over the last 2 millennia, the 20th century experienced an unprecedented rise. This suggests that today's climate is likely the warmest in at least 2,000 years. Compared to the medieval warm period and the Little Ice Age, the recent warming is notable for its speed and magnitude. Examining the last 10,000 years shows that current temperatures are reaching record levels, continuing a steep upward trend. Ice core data indicate that over the past million years, Earth has gone through cycles of ice ages and interglacials, driven by Milankovitch cycles, which refer to changes in Earth's orbit and tilt occurring over thousands of years. Following the last ice age, temperatures rose by 4 to 7 degrees Celsius over 5,000 years, whereas in just the past century, temperatures have increased by about 1.4 degrees Celsius, 20 times faster than during that ancient transition. Models predict further warming of 2 to 6 degrees Celsius in the next century, a rate 20 to 60 times faster than historical events, raising concerns about its cause. Going back even further, geological evidence shows extreme warmth during the age of dinosaurs and extreme cold during snowball Earth phases. However, the current rate of warming is faster than anything seen in those past events. Importantly, today's climate is part of a dramatic uptrend. If current trends continue, we could witness even more significant changes compared to historical patterns, indicating that what we're experiencing is just the beginning of a larger shift. Understanding Earth's climate begins with the concept of energy balance. Earth receives energy from the sun, primarily as visible light and ultraviolet radiation, averaging about 240 watts per square meter. This energy heats the planet, but Earth also radiates energy back into space in the form of infrared radiation. According to the Stefan-Boltzmann law, the rate at which Earth radiates energy increases rapidly with temperature. Without an atmosphere, Earth's average temperature would be around -18 degrees Celsius, too cold for life as we know it. However, the atmosphere contains greenhouse gases, such as water vapor and carbon dioxide, which trap some of the outgoing infrared radiation, keeping Earth warmer, a phenomenon known as the greenhouse effect. Although the atmosphere is mostly nitrogen, 78%, and oxygen, 21%, small amounts of greenhouse gases play a crucial role in maintaining Earth's average temperature of about 15 degrees Celsius. Water vapor contributes roughly half to 3/4 of the greenhouse effect, while carbon dioxide accounts for about 1/5 to 1/4. Greenhouse gases not only trap heat, but also re-radiate some of it back to the surface, ensuring that energy eventually escapes into space. This balance is vital for a stable climate. Additionally, the cooler upper atmosphere cannot radiate as much energy as the warmer surface, creating a temperature gradient that supports the greenhouse effect. Earth's energy budget is a complex system. Sunlight is partially reflected back into space by clouds, particles, and reflective surfaces like ice, while the rest is absorbed, warming the planet. This energy is then radiated as infrared radiation. Greenhouse gases trap much of this heat, re-radiating it towards both the surface and space. Energy transfer also occurs through thermals and evapotranspiration, contributing to the greenhouse effect and maintaining a climate suitable for life. Disruptions to this balance, such as increasing greenhouse gas concentrations, altering incoming sunlight, or changing Earth's reflectivity, can significantly impact energy balance and climate, underscoring the delicate interplay of factors that regulate our planet's climate system. How do we know that greenhouse gases are driving Earth's warming? Alongside advanced experimental data and sophisticated climate models, we rely on historical climate records to understand greenhouse gases' role in our climate. Water vapor, though the dominant greenhouse gas, remains in the atmosphere relatively briefly, and it primarily acts as a feedback mechanism, amplifying warming initiated by CO₂. Carbon dioxide, in contrast, stays for centuries, making it a key factor in long-term climate change. Ice cores trap ancient air, allowing scientists to measure past greenhouse gas levels. Data from the past 500,000 years show a close correlation between CO₂ levels and global temperatures. During ice ages, CO₂ levels were low, and temperatures were cooler, while interglacial periods saw higher CO₂ levels and warmer conditions. This pattern confirms CO₂ as a significant driver of Earth's climate. The same correlation holds when we look back 800,000 years, showing how both CO₂ and methane rise and fall alongside temperature fluctuations. However, this relationship isn't simple cause and effect, it involves a complex feedback loop. Initial temperature changes, often triggered by orbital shifts, cause CO₂ stored in oceans and soils to be released, intensifying warming. This positive feedback drives further temperature increases, illustrating how interconnected greenhouse gases and Earth's climate are. The reverse feedback occurs as cooling orbital changes lead to CO₂ absorption, gradually driving temperatures down. Looking deeper into Earth's history, around 60 to 200 million years ago, CO₂ levels exceeded 2,000 ppm, leading to a much warmer planet, where tropical ecosystems thrived in polar regions. This warmth was largely due to volcanic activity and the breakup of Pangaea. Over these vast timescales, geological processes like volcanic eruptions and tectonics were major climate influencers. The sun has also played a role in climate shifts. Its output varies, affecting Earth's climate on different time scales. For instance, the 11-year solar cycle can cause short-term climate variations, while longer-term cycles, like Milankovitch cycles, lead to glacial and interglacial periods. One notable example of short-term climate change is the Little Ice Age, 1300 to 1850 AD, which saw global temperatures drop by 1 to 2 degrees Celsius. The Maunder Minimum, a period of reduced solar activity, contributed to this cooling, but volcanic activity and oceanic changes were also significant factors, illustrating the complex web of influences shaping Earth's climate over time. The greenhouse effect isn't unique to Earth, it's a universal principle. A comparison of Venus, Earth, and Mars highlights how atmospheric composition determines a planet's climate. Without greenhouse effects, Venus should be around 55 degrees Celsius, Earth minus 18 degrees Celsius, and Mars minus 50 degrees Celsius. However, Venus has a surface temperature of 460 degrees Celsius due to its thick, CO₂-rich atmosphere, while Earth averages 15 degrees Celsius, and Mars remains frigid at minus 60 degrees Celsius with its thin atmosphere. Venus, with 96% CO₂, experienced a runaway greenhouse effect. As temperatures rose, water vapor amplified the effect, eventually leading to water loss through photodissociation. Volcanic activity further increased CO₂ levels. Mars, with little atmospheric insulation, lacks a significant greenhouse effect, keeping it cold. Earth's moderate greenhouse effect keeps it in a stable, life-supporting zone, showing how atmospheric greenhouse gases, especially CO₂, are key to shaping planetary climates. Water vapor and carbon dioxide naturally cycle through Earth's system, influencing the climate. Water vapor, although it stays in the atmosphere for only about a week, adjusts quickly to temperature changes, playing a vital role in regulating the greenhouse effect. Carbon dioxide cycles more slowly and remains in the atmosphere for decades to centuries, making its impact long-lasting. The short-term carbon cycle involves rapid exchanges of CO₂ between the atmosphere, oceans, and living organisms. For instance, carbon dioxide dissolves in surface ocean waters, and this process is balanced by CO₂ released back into the atmosphere. Plants absorb about 120 gigatons of CO₂ per year during photosynthesis, converting it into carbohydrates. Respiration and decay return most of this carbon to the atmosphere. Although some carbon is stored in soils and oceans, the short-term carbon cycle maintains a natural balance, with CO₂ levels in the atmosphere remaining stable over time, provided there is no human interference. In this rapid cycle, a typical carbon dioxide molecule stays in the atmosphere for about 5 years before being cycled back out, though some carbon ends up stored in soils and oceans. In the long-term carbon cycle, CO₂ can persist in the atmosphere for much longer due to processes like the biological pump and deep ocean circulation. Marine organisms carry carbon to the deep ocean when they die, where it is stored in sediments. The deep ocean holds about 37,000 gigatons of carbon. While some carbon eventually returns to the surface through upwelling and diffusion, around 2 gigatons per year are removed from the surface and sequestered in the deep ocean. CO₂ can remain in this cycle for hundreds to thousands of years, with some molecules potentially persisting for up to 30,000 years. This slow carbon exchange affects global temperatures and amplifies the greenhouse effect over long periods. Additionally, geological processes such as the formation of sedimentary rocks and volcanic activity operate over millions of years. Carbon that sinks into the deep ocean becomes part of rocks, which later return to the surface through tectonic activity. Weathering or volcanic eruptions release this stored carbon back into the atmosphere. Fossil fuels like coal, oil, and natural gas, which hold around 10,000 gigatons of carbon, also play a crucial role when burned by humans, releasing ancient carbon back into the atmosphere and influencing climate change. Let's take a closer look at the human role in climate change. Is there solid evidence that human activities are driving the recent rise in global temperatures, and how does this compare with natural causes like the sun and volcanoes? The natural carbon cycle efficiently circulates carbon between the atmosphere, oceans, and living organisms. However, human activities have disrupted this balance. Burning fossil fuels adds about 7 gigatons of CO₂ to the atmosphere annually, while deforestation contributes another 2 gigatons. These 9 gigatons may seem small compared to natural carbon flows, but they accumulate over time, enhancing the greenhouse effect. Before the Industrial Revolution, the atmosphere contained around 560 gigatons of carbon. Today, that number has risen to about 800 gigatons, with a net effect of 4 gigatons of CO₂ added to the atmosphere each year. CO₂ levels have risen from 280 parts per million ppm in 1750 to around 420 ppm today, a 50% increase largely due to human activities like fossil fuel burning and deforestation. Thanks to precise measurements, we can see both the overall rise in CO₂ and subtle seasonal fluctuations. These wiggles reflect the cycle of photosynthesis. Plants absorb CO₂ in spring and summer on the land-predominated northern hemisphere, causing levels to drop, while in winter, levels rise again. This pattern, overlaid on the long-term upward trend, highlights the ongoing increase in CO₂, a clear sign of the enhanced greenhouse effect driving global warming. But how do we know this rise is due to humans? First, fossil fuel sales data aligns with CO₂ increases. Second, carbon isotopes show a shift toward the low carbon 12, a typical signature of fossil fuels. Lastly, fossil fuel combustion consumes oxygen, leading to measurable decreases in atmospheric oxygen. Looking back over 1,000 years, CO₂ levels remained stable until the Industrial Revolution, when they began to rise sharply. This increase, especially over the last century, is unprecedented. Extending further back over the last 800,000 years, CO₂ levels naturally fluctuated between 180 and 280 ppm, tied to ice ages and interglacial periods. Today's level of 420 ppm far exceeds anything observed in natural cycles, likely the highest in at least a million years, signaling a significant human impact on Earth's climate. Carbon dioxide isn't the only human influence on Earth's climate. Other factors also affect the planet's energy balance. Methane is about 26 times more effective than CO₂ at trapping heat, though it stays in the atmosphere for only about 9 years. Its sources include leaks from natural gas systems, agriculture, and decaying vegetation in reservoirs. Methane contributes to roughly a third of global warming. Aerosols, like soot and sulfate particles from industrial activities, reflect sunlight and cool the climate. They also promote cloud formation, further increasing sunlight reflection. However, this cooling is localized and insufficient to counteract global warming. Gases like nitrogen oxides, halocarbons, used in refrigerants, and ozone also affect the climate. Ozone in the lower atmosphere warms, while in the upper atmosphere it cools. Deforestation and urbanization impact Earth's reflectivity. While deforestation can slightly cool the climate by increasing albedo, urbanization typically leads to warming. Overall, these changes contribute more to warming than cooling, especially when considering greenhouse gas emissions. Natural factors like solar intensity do play a role in Earth's climate, but their impact on recent warming is minor compared to human activities, which remain the dominant cause of climate change. Some skeptics suggest that the sun might be responsible for global warming, but evidence shows otherwise. While solar energy output does fluctuate, if the sun were causing current warming, we would see uniform heating across all atmospheric layers. Instead, we observe cooling in the upper atmosphere, the stratosphere, and warming at the surface, a pattern consistent with the greenhouse effect, where gases trap heat in the lower atmosphere. This stratospheric cooling is a key piece of evidence supporting greenhouse gas-induced warming. Additionally, climate models that only account for solar variations cannot replicate the observed warming of the past century. Although solar activity has decreased since the 1960s, global temperatures continue to rise, highlighting that the sun is not the main driver. Volcanic activity, which emits CO₂, also cannot explain the warming trend. Volcanic CO₂ emissions are less than 1% of those from human activities. Moreover, eruptions tend to have a short-term cooling effect due to the ash and sulfur dioxide they release, which reflects sunlight. While volcanism played a role in ancient climate shifts, today's warming is overwhelmingly driven by human greenhouse gas emissions. Advanced climate models further support this. When simulations include only natural factors like solar activity and volcanic eruptions, they explain past climate variations, but not the rapid warming since the mid-20th century. Only when human influences, such as greenhouse gas emissions, are added do the models accurately replicate recent temperature trends, strongly pointing to human activities as the main cause. Why is climate change such a big concern? Even a small rise in global temperatures can lead to dramatic environmental shifts. In 2015, the Paris Agreement set the goal of limiting global warming to well below 2 degrees Celsius, aiming for 1.5 degrees Celsius. However, current commitments may still lead to a 2.5 to 2.9 degrees Celsius rise by 2100. To meet the 1.5 degrees Celsius target, emissions need to peak by 2025. A small global temperature rise can have significant effects, especially on land where warming can be nearly twice as much, and even more in the Arctic. Key impacts include weather patterns, increased heat waves, droughts, and stronger storms. Drylands could cover up to 56% of Earth's continents, affecting water supplies and crops. Sea level rise. Oceans are rising due to expanding water and melting ice. Sea levels could rise 30 to 120 centimeters by 2100, threatening coastal regions and displacing millions. Ocean changes. Ocean acidification is harming marine life, especially coral reefs. Warming and changing currents disrupt marine ecosystems and oxygen levels, creating dead zones. Wildfires. Warmer temperatures and dry conditions are fueling more frequent and intense wildfires. Changing biomes. Ecosystems are shifting, threatening biodiversity as species struggle to adapt or migrate. Extinction risk. Species unable to adapt face extinction, with coral reefs, polar bears, and amphibians among the most vulnerable. Human health. Heat waves, disease spread, and extreme weather threaten human health and livelihoods, while climate change drives migration and creates climate refugees. Agriculture. Crop yields are declining due to heat stress, droughts, and shifting pest patterns, affecting food security. Tipping points. Potential tipping points, such as ice sheet collapse or permafrost methane release, could trigger irreversible changes and accelerate global warming. Climate change's impacts are wide-ranging and costly, affecting ecosystems, economies, and human well-being. Our biggest impact on climate comes from energy consumption. The world currently uses around 20 terawatts, which equates to 180,000 terawatt-hours annually, and equals 2,500 watts per person. In energy-intensive countries like the US and Canada, this figure exceeds 8,500 watts per person. Energy is used across four main sectors. Transportation, 35%. Industry, 31%. Residential, 20%. Services, 14%. In 2023, fossil fuels still dominate, making up 82.5% of energy use, while renewables contribute 14%. The share of renewables, especially solar and wind, has risen from 0.7% in 2000 to 7.7% today. In electricity production, renewables now account for 13.4%. CO₂ emissions from energy and industry have shifted over time. Early industrialization was driven by coal, with oil and gas rising by the late 1800s. Today, solid, liquid, and gas fuels dominate global emissions, while cement and flaring play smaller roles. Coal emissions have declined in Europe and the US but surged in countries like China, India, and South Africa. Energy use often correlates with economic prosperity, but efficient countries can achieve high GDP with lower energy consumption. Some economists argue the Human Development Index, HDI, better measures well-being than GDP, highlighting that beyond a certain point, more energy doesn't necessarily improve quality of life. True progress may lie in using energy more wisely, not just using more. As we confront climate change, transitioning away from fossil fuels is essential. Earth's natural systems offer various energy sources, each with pros and cons. Solar energy is by far the largest, providing more energy to Earth in an hour than humanity uses in a year. Geothermal and tidal energy make up smaller portions. Fossil fuels, which means coal, oil, and gas, store ancient solar energy, while nuclear fuels like uranium release energy through nuclear fission. There's potential for nuclear fusion, which could provide nearly limitless clean energy, though it's still under development. Currently, fossil fuels dominate our energy mix, despite their environmental harm, including air pollution that causes 4.5 million premature deaths annually. They are also unevenly distributed, making countries reliant on imports. Additionally, oil and gas reserves are expected to dwindle in the coming decades, potentially leading to shortages and economic instability. Nuclear fission provides reliable low-carbon electricity, but safety concerns and radioactive waste management are challenges. Nuclear fusion offers promise but remains experimental. Renewable energy sources like solar and wind are growing rapidly. Solar power has become one of the cheapest electricity sources, and wind energy is also seeing significant cost reductions. Hydropower is well established, though its expansion is limited, while tidal and wave energy are still developing. Geothermal energy also plays a role, providing a reliable, consistent source of renewable power. However, it is geographically limited to areas with high volcanic or tectonic activity, which restricts its broader use. Biomass holds potential as renewable fuel, especially for transportation, though its environmental benefits depend on how it is produced. Hydrogen is a clean fuel, producing only water when burned. However, it must be produced from other energy sources, so its environmental impact depends on how it's made. For hydrogen to play a major future role, it needs to be generated from renewable or nuclear sources. While no energy source is without challenges, the future also depends on electrification. Shifting sectors like transportation and heating to renewable electricity is key to reducing fossil fuel use and achieving net zero emissions. To stabilize greenhouse gas concentrations and address climate change, we need to avoid dangerous CO₂ levels. Pre-industrial CO₂ was about 280 ppm, and doubling it to 560 ppm is a critical risk threshold. Current levels are around 420 ppm, and rising by 2.5 ppm annually, putting us on track to surpass 500 ppm, which could lead to a 3 degrees Celsius rise in global temperatures even before 2100. Several strategies to mitigate this include: 1. Geoengineering. Proposals like orbital mirrors, sulfur injection, and ocean fertilization to reflect sunlight or absorb CO₂, but these are speculative and risky. 2. Carbon capture. Technologies to capture CO₂ from plants or the air, such as direct air capture or DAC, combined with sequestration in geological formations or the ocean. 3. Alternative energy. Transitioning to low-carbon sources like nuclear, solar, wind, and hydroelectricity. Solar and wind, in particular, have seen rapid cost reductions and capacity growth. 4. Energy efficiency, improving insulation, using energy-efficient appliances, and optimizing industrial processes to reduce energy demand and emissions. 5. Reforestation, protecting forests and replanting trees to absorb CO₂ naturally and help restore carbon balance. No single solution can solve climate change. A comprehensive, multi-pronged approach is essential. In conclusion, the current rise in global temperatures is highly unusual, far exceeding natural variations over thousands of years. This warming is driven by skyrocketing greenhouse gas levels, primarily from fossil fuel combustion, and is evident in alarming signs like melting polar ice and rising sea levels. Climate change poses significant threats to both humanity and the environment, including extreme weather events that can lead to devastating natural disasters, food and water scarcity due to shifting agricultural zones, and the loss of biodiversity as ecosystems struggle to adapt. Vulnerable communities are particularly at risk, facing displacement and health issues as climate impacts worsen. To counter this, we must urgently reduce emissions and explore ways to remove carbon from the atmosphere. A comprehensive shift to renewable energy and increased energy efficiency is essential to mitigate climate change and secure a sustainable future. The time to act is now. If you want to learn more details for the climate change, you can watch my video Climate Change and Global Warming, a complete guide.